All right, in this lecture, I'm going to talk about probability. You really can't talk about statistics without talking about probability because notions about likely outcomes and their relative frequency definitely undergird our approach to statistics and is definitely relevant to the hypothesis testing framework that guides our notions of statistical significance. So there's lots of reasons to learn about probability, which is just basically evaluating the odds of any certain number of outcomes happening. One is, like I said, it's definitely conceptually related to doing statistics generally. Every time you run a statistical analysis, there's some element of evaluating the probability of that outcome. Additionally, learning about probability can sort of help you in life in general in ways that maybe fancier statistics won't. Things like helping guide your decision making, anything from what's my risk of getting coronavirus to what's the chance that I win the lottery. Any number of possible outcomes, we're often interested in sort of trying to make as accurate predictions as possible. Understanding and calculating probability is basically a simple way to do that. So let's get right into it. As I mentioned, ideas about chance or probability are highly conceptually important in the process of inferential statistics. So anytime you evaluate for statistical significance, you're essentially making statements about probability. If you've ever heard of a p-value, that's a probability value. It really means something in terms of probability. We can define probability as a way of trying to understand, describe, and possibly predict random events. So basically, if there's certain outcomes that we know are hypothetically possible, what's the likelihood of any given outcome occurring? Since there's no such thing as perfectly predicting the future, in general, probability is going to be more useful to help us predict what we would call relative frequency of events. So if you, let's say, roll the dice 6 times, the idea is you have a 1 in 6 chance of landing on any particular face of the dice, but that doesn't mean that if you roll the dice 6 times, you're definitely going to get a 1, a 2, a 3, a 4, a 5, or 6. So basically, it's sort of more so the case that if you were to roll the dice many, many, many times, you would see that over the long term, each face of the dice has a 1 in 6 chance over the long term of being landed on any particular turn. So if you're only rolling the dice a few times, it's going to be harder to use those probabilities to make predictions about what's going to happen. So probability is all about relative frequency over the long term. And when I say relative frequency, this is basically how often any particular event or outcome you're interested in will occur given all the theoretically possible events. So here's a really simple probability example. Let's say there's a certain number of students enrolled in a typical semester of Psych 293. I decide to randomly pick one student to give a puppy to. Not that beautiful puppy on the top, but maybe a similar looking teddy bear puppy like the one on the bottom. You might think to yourself, what are the odds that I'm the lucky winner? You have to think about which outcome you're interested in and all of the possible outcomes. Given there's 93 people in the class, those are 93 possible outcomes since I'm only selecting one winner. If you're interested in the probability of you specifically being the winner, well, there's only one outcome that would represent that particular reality. So you have a 1 in 93 chance of being the winner. You can take that information and you can put it into different probability terms. Probabilities can be depicted in their terms as a fraction, so 1 out of 93. You can actually divide that fraction to put your probability into that decimal format you see, so 0.0108. You can leave your probability terms like that, but what that corresponds to in percentage terms, you would need to carry that decimal place 2 spots over, meaning that your probability of being the winner of the puppy contest is 1.08%. So all of those are valid ways of depicting the same probability information. In general, this is going to be the basic framework for putting together your probability computation. So the probability of any specific event that you're trying to predict occurring is going to be this basic fraction where you identify the number of events that qualify as an A outcome over the total possible number of events. So you tweak this depending on what you are currently classifying as a successful event. If, let's say, you were just trying to figure out the probability of picking someone on the far left side of the class, you would just have to know how many people were on the far left of the class and then divide over that same total number of students. So you need to think about how many events would constitute a success or the outcome that you're trying to predict over the total possible number of events. So this basic framework for probability of depicting odds of a certain thing happening out of all possible outcomes, we're bombarded with statistics like this all the time. Things like, what are the odds of winning the lottery? What are my odds of being struck by lightning? What are my odds of being attacked by a shark? What are the odds that a woman gives birth to quadruplets? So these are all seemingly rare events that we're somewhat interested in understanding realistically what are the odds that this is going to happen to me in my lifetime. One point that I would like to make here is that you can't just sort of look at probability odds completely objectively. The fact is that as humans, we have our own priorities and our ideas about what sorts of outcomes we want and whether or not we value them. You might be looking at those odds of winning the Mega Millions jackpot and think to yourself, why does anyone ever play the lottery? Those odds are astronomically unlikely. You're far more likely to be attacked by a shark or get hit by lightning than winning the lottery. The reason is because humans have their own motivations and perspectives on events. The lottery, you kind of pay to play. It's just sort of the fun of the experience. So people do it because they enjoy it. So they don't care that they know that it's exceedingly unlikely. They just sort of like the fantasy. That's part of what you pay for when you buy a lottery ticket. Additionally, you have to look through the lens of the certain outcomes that people want or don't want, right? What are the possible outcomes that happen if you buy a lottery ticket? You either win, which has a huge upshot, or you lose and you're out a couple bucks. That sort of cost benefit analysis imbues all of these objective probability statistics with meaning. So, anytime you're presented with a probability, the idea is you don't necessarily need to divorce that probability from your own biases and perspectives because you can use that to think more realistically about what you want to do, what you don't want to do, what you should or should not be afraid of. Additionally, one feature of the fact that probabilities put things into these proportional terms is that you can apply the probability to any hypothetical number of individuals. So let's say you were interested in lightning strike statistics, and maybe you were a New Orleans Saints superfan, and you were interested in applying those lightning strike statistics to a full Superdome full of Saints fans. Well, what you would do is you would take that capacity, so the number of people that it would take to fill the Superdome, and what you can do is you can use that fraction, that probability, to apply to that capacity to get an understanding of how many people from a full Superdome will get struck by lightning in their lifetime. You just have to apply those proportional odds to the number of people currently under consideration, and you would be left with the conclusion that around 5 people from a full Superdome crowd are going to get struck by lightning in their lifetime. This is, again, not perfect predictive accuracy. It's perfectly acceptable in realistic terms that 4 people get struck by lightning or a very unlucky crowd has more than that. This is about relative frequency. And again, the basic idea here is that you can apply your probability to any hypothetical number of people. So to walk through the various approaches for calculating probability, I'm going to use some really simple probability type examples. So when I say simple probabilities, things like what are your likelihood of pulling a certain card from a deck, pulling a certain marble out of a bag, those sorts of really simple probability scenarios help demonstrate the various ways that you can calculate probability for yourself. So here's an example. Let's say I draw one card from a deck of cards and I ask what's the probability of drawing an ace or a king. Again, the key approach here is to figure out how many events would constitute a quote unquote success. So you're trying to predict the likelihood of a king or an ace. So you need to know how many kings and aces there are. If you know anything about a deck of cards, you know that overall there are 4 kings, 4 aces, and so you have 8 qualifying events, and a full deck of cards has 52 cards in them. So the idea is you have an 8 out of 52 chance of pulling a king or an ace out of the deck. Again, you can take this fraction and put it into its decimal type presentation, and you can transfer that into its percentage terms. Again, that fraction, you can turn it into that decimal presentation, or the percentage, they mean the same thing. Now, some logical principles of probability calculations to help make sure you're never steered wrong in your computations. One is that the total number of possible events includes all of the quote unquote successful, or characterized as A events. Basically, if you're trying to divide a certain subset of events over the total possible number of events, the number of A events cannot exceed the total number of possible events. Even something that happens 100% of the time, that would mean that all events A is the same number of theoretically possible events. So for this reason, a probability can never exceed 100%. It is impossible for the probability of something happening to exceed 100% because 100% means something happens every time, and there's no more times than that. Additionally, the number of potential events can never be negative. If we're talking about number of times something happens, events can happen 0 times, and they can only go up from there. There's no such thing as an event happening a negative amount of times. If an event never happens, that's 0 times. So there's no such thing as a negative probability because it is never the case that something can happen fewer than 0 times. So when you calculate your probability, it will always be between the range of 0 to 1, which corresponds to a spectrum of 0% of the time something happens to 100% of the time. So if you ever calculate a probability outside of those boundaries, you did something wrong. On the back of that sort of logical conclusion, you can take that a step further. Again, if a probability of an event is that it always happens, that means that every time an event occurs, event A is occurring. That's something happening 100% of the time. So the closer your probability gets to 1, the more likely your event is to happen. A probability of 0, again, corresponds to that event you're trying to quantify, never happening, or 0%. Additionally, you can use this logical framework to calculate the probability of something not happening. Since the only possible logical outcomes is for something to either happen or not happen, one of those two things has to happen, that means that the probability of something not happening and something happening adds up to 100%. For this reason, if you know the probability of something happening, you can very easily get the probability of it not happening by subtracting the probability of it happening, that probability of A, subtracting that from 1. In this case, this 1 stands in for a 1-to-1 probability, meaning 100% of the time, because PA plus P not A necessarily adds up to 100%. So you can use the construction of that equation to figure out the probability of something not happening by subtracting the probability of it happening from 1. Again, think about this. In your lifetime, you either will get struck by lightning or you won't. So if you followed along with that Superdome example, and I mentioned a certain proportion of people in the Superdome who are likely to get struck in their lifetime by lightning, the idea is that remainder of the people represent all the people in the Superdome who will not get struck by lightning. So you can switch back and forth very easily from the probability of something happening and it not happening, due to the fact that logically the probability of an event happening and an event not happening, given that that covers all possible outcomes, adds up to 100%. Again, I mentioned this earlier, but the probability describes relative frequency of events over the long term. That means that if you're just trying to predict an event on one specific instance, your probability is not going to be able to perfectly tell you what's going to happen on each trial. What it does tell you is about the probability of things over the long term. So it's important to keep in mind that if you know the probability of something happening, but you only run that trial a few times, you might not see your outcomes perfectly map onto the underlying probability. But the more trials you run, the more coin flips you do, the more times you roll the dice, the more often you're going to see your outcomes approach the underlying probability distribution. So computing probability is going to depend on the nature of the event you're trying to predict. So in some instances, probability computation is going to be subject to what we call the addition rule. This is going to be used when we want to know the probability of one event or another event occurring. So the probability of an event A or an event B. Basically, if we want to know the likelihood of one event or another event happening, we can basically add together the probabilities of each of those events happening by themselves and just add them together to get the probability of either one happening. There's going to be a slight distinction on how exactly you're going to employ the addition rule, depending on whether or not events A and B can simultaneously occur on a single trial. But no matter what, if you're trying to find one event or an event's probability of happening, in general, you're going to want to use the addition rule. If we're dealing with what we call mutually exclusive events, meaning that A and B cannot simultaneously co-occur on a single trial, for example, on any given coin flip, you're going to flip a heads or a tails. It is impossible for the heads event A or a tails event B to simultaneously co-occur. That means that those outcomes are mutually exclusive. So let's say I have a bag full of 9 colorful marbles. I know how many are red, how many are blue, and how many are yellow. Now on each given pull, you're going to pull a single marble. So it would be impossible to pull a red and a blue simultaneously because all of the marbles in this example are a single color. So it would be impossible to simultaneously in a single marble pull get a marble that was both red and yellow. That means that a red and a yellow marble on a given pull are mutually exclusive. So you use your very basic addition rule to compute this. You know that 4 out of the 9 marbles are red. You know 3 out of the 9 marbles are yellow. You just simply add those fractions together. So in this case, the probability of getting a red or yellow marble, 7 out of 9. Again, this corresponds to a probability of 0.78. Now, there are some instances wherein the different outcomes you're trying to predict could co-occur on a single trial. This would be referred to as a non-mutually exclusive event. So let's say for this example, we're playing pool and you sink one ball on the break. What's the probability that the ball is striped or red? So you want to know the probability of getting a striped ball and the probability of getting a red ball. There are 7 out of 15 striped balls, and there are 2 out of 15 red balls. The red balls are the ones here. Those are technically burgundy, I believe. So if we're talking red, we're talking about that 3 and that 11. So the basic idea is that we can't quite use that exact rule that we used previously of the addition rule. If we did, we would just add those two probabilities together. Here's the problem. It would be possible to get a striped and red ball on the same pocket. Given that there's one ball, the 11, that is both striped and red, if we merely add together the probability of getting red balls or striped balls, we're inadvertently counting that 11 ball twice, and that distorts the accuracy of our probability. So we don't want to count that ball twice, so we need to correct for the fact that it's part of the striped probability and the red probability. We basically just want to correct for that double count. So you do just that. You modify the rule by adding together the probability of A and probability of B, but then you just subtract out that non-mutually exclusive event. So in this case, you take the probability for getting a striped ball plus the probability of getting a red ball, and then you just subtract 1 out of 15 to make sure that that 11 ball isn't counted twice. So your actual probability of getting a striped or red ball is 8 out of 15, or 0.53. In other instances, your probability is going to be subject to what we call the multiplication rule. This is when we want to know the probability of multiple events co-occurring. So not one event or another event happening, but one event and another event happening. So in this case, we want to know the probability of event A and event B happening. So in this case, we're going to use a slightly tweaked rule where we multiply probabilities together. We're going to want to know the probability that event A occurs, and we're going to multiply that by the probability that event B occurs, given the assumption that event A occurs. So this one's a little bit more complicated, but it's pretty easy. I'll basically show you what I mean. The value of that second probability, that probability of B happening assuming A already happened, is going to depend on whether or not your A and your sequential B event are what we call independent of one another. This would be the case if event A and event B have no effect on one another. Basically, whatever happens on A has no bearing on the probability of event B happening. In this case, your multiplication rule is going to simplify to multiplying probability of A by probability of event B. Okay, so if, for example, you've got a bag of marbles, you pull one marble out, you put it back in the bag, and then you pull another one, we would consider those completely separate events. The thing that happens in event B is not impacted by what happened on event A. So if you want to know the probability of your first event happening and then your second event happening, you just need to figure out the probability of each of those events independently and then multiply them together. Okay, so let's take the example of some coin tosses. What's the probability of getting 2 heads in a row? On any given coin toss, you know that there's a 1 in 2 chance of getting a heads. It's 50-50. There's only 2 possible outcomes. The probability of getting heads on the second time is the same. The second coin flip doesn't care what happened on the first coin flip. Nothing about the coin changes based on the number of flips that you do. So event B is completely independent of event A. Now you still want to know what the probability of these events co-occurring is, so you do multiply those two probabilities together. But again, think about it. You flip a coin once, and you flip a coin again. Having done that first coin flip doesn't actually change anything about the coin itself. As such, each coin flip can be thought of as an independent event. So we can use our most simple multiplication rule to multiply 0.5 by 0.5 to get that the probability of getting 2 heads in a row, i.e. a head co-occurring with a second head, as 25%. The independence of your various events is going to depend on what we call your sampling. Basically, what sort of way you're pulling marbles out of the bag or pulling cards out of a deck. If you're sampling with replacement, this is when each event, after each event is completed, the scenario is returned to its original state. So, for the pulling the card example, if you pull one card on the first pull, you return it to the deck, and then you select another card, you are sampling with replacement. So we take one card, we figure out whether or not we hit the qualifying or successful event. We then return the cards to their original state such that there are still 52 cards in the deck. That would be a completely independent set of events. A coin flip's another example of this. You flip a coin, you flip it again. The coin itself does not change every time you flip the coin. So these would be examples of independent events because you are sampling with replacement. Okay, so another example, let's say we have our same bag full of colored marbles. 4 are red, 2 are blue, 3 are yellow. If 2 balls are selected, what's the probability that they will both be red? So if we're sampling with replacement, i.e. we're putting each marble back after we pull it, we know that the probability of getting a red marble in the first place is 4 out of 9. The probability of getting a marble in the second place, still 4 out of 9. Because the assumption is if you get that first red marble and you return it to the bag, you have returned that bag to its original state, whereby there's still 4 red marbles and there's still 9 marbles overall. So again, in this case, you are sampling with replacement, meaning the events are independent, meaning that you can just multiply the probability of event A and event B together very simply. Now, it might be the case that you're computing the probability of certain events that are not independent of one another, for example, by sampling without replacement. This would be after each event, you are not returning that outcome to the population from which it was derived, or you're not returning the environment to its original state. So something about the population that you're sampling from is changing on each draw, on each trial. So to use this marble example, sampling without replacement using the marble bag would have us drawing one marble and then throwing it away, and then drawing a second. Each time you pull out a marble and you throw it away, you are changing what's going on with that bag of marbles. You are changing how many marbles are left in the bag. You're essentially iteratively changing what is true about the bag on each draw by sampling without replacement. So what would you do in this case? You would need to think about how the bag of marbles changes on the second draw. Your probability of getting a marble on the first draw, still 4 out of 9. But think about what happens should you make it past that first hurdle. Let's say you pull one red marble out of the bag and you throw it away. That leaves 3 red marbles in a bag of 8 marbles. So the probability of event B happening is actually 3 out of 8. So in this case, if we're sampling without replacement, the probability changes on each iterative trial, meaning that the probability of each event is going to look a little bit different than the one before it. Still though, you use the multiplication rule. The probability of getting 2 red marbles in a row is still going to be derived by multiplying those 2 probabilities together, but crucially, notice how that 4 out of 9 became a 3 out of 8, reflecting the fact that you did not replace the marble to the bag after that first draw. Now we can make things even more complicated. Let's say you have more than 2 unique events that you're trying to predict. Let's say you're dealt a 5-card hand from a deck of cards. What's the probability that all 5 cards will be clubs? Now you're going to be doing 5 trials, and again, you are going to be sampling without replacement. So if you take the first card is a club probability, there's 13 clubs and 52 cards, that first probability, 13 out of 52. Now let's say I take that first club and I throw it away. The next trial, there are only 12 clubs left in the deck, and there's only 51 cards left. Now imagine the probability as it would change on 5 sequential card pulls. By the third pull, there's only 11 clubs left out of a deck of 50. On the fourth, there's only 10 clubs left out of a deck of 49. And then the fifth draw, there's only 9 clubs left out of 48 cards. So again, see how those probabilities iteratively change on each draw. If you had been replacing the card after each draw, the probability would remain 13 out of 52 on each one of these draws. Since in this case, in this example, we are sampling without replacement, so assuming that we get our first club, throw it away, we get our second club, throw it away, you see these probabilities changing iteratively on each draw. So you're still using your multiplication rule since you're trying to predict multiple events co-occurring. You want event A and event B and event C and D and E all to happen. So to do that, you multiply all those probabilities together. So all those probabilities I got in the last slide, you again subject them to the multiplication rule. You are left with a pretty vanishingly small chance of getting 5 clubs in a row. To be exact, less than 1% or 0.05%. Now, there might be some cases in which both the addition and multiplication rules are in effect. Here's an example. What's the probability of getting any flush in a 5-card hand? So we just computed the probability of getting a club flush, and obviously it was quite small. What if we were to open the door to say we will accept a flush of any hand? So a flush is going to involve events co-occurring, but we'd be willing to accept a flush of clubs or spades or hearts or diamonds. That means we will be combining the addition and multiplication rules, because once we know the probability of getting a single flush, we combine those probabilities together to figure out the odds of getting any flush. So basically, to do that, we'd need to know the probability of getting a heart flush, a diamond flush, a club flush, or a spade flush. The probability of each one of those flushes individually is the same as the club one we just computed. Basically, it's needing to get 5 cards of a single hand or suit. Is that what it's called? Any of those flushes you would accept as a successful event, but the probability of getting a heart flush is the same probability as getting a club flush. So in this case, we take that probability for clubs that we computed using the multiplication rule, and you add it together 4 times. This yields us a 0.2% chance of getting a flush of any hand. So the odds are higher than it was of getting a specific flush, not by much, but you did add together those probabilities once you derived the probability of getting any individual flush using the multiplication rule. So a few last conceptual points to wrap up this section on probability. So these methods basically are meant to allow us to predict the probability of any particular outcomes or events that we're interested in on any particular trial. In general, when we're doing statistics, we're interested in our underlying probability distribution that describes all possible outcomes. So when we're talking about statistics, we're inherently going to be dealing with what we call probability distributions. This is basically an underlying or theoretical distribution of the relative likelihood of all possible events. But if we're talking about statistics, we're talking about events, meaning statistical outcomes. So whenever we compute a Pearson's R or a T from a t-test, the idea is there's a certain number of theoretically possible t-test outcomes. Once we compute our actual obtained t-statistic, we're going to want to know what were the odds of that particular outcome. We do this by comparing our obtained statistics to their underlying theoretical probability distributions. One example of this that we can use is just the normal distribution. This is again a theoretical probability distribution that provides a probability spread for various events. So if we have data that's relatively normally distributed, we can use this probability distribution to generate some predictions using probabilities. So say, for example, we know the mean on a test is 80, standard deviation of 7. We can ask ourselves, if we were to randomly sample one score from the people that took the test, what's the probability that will be as high or higher than a score of 89? You can use the normal distribution. You can transform that raw score that you're trying to predict into a z-score, and you can map it onto the normal distribution, which, as you know, you can take that z and you can transform it into a percentage. So essentially, you can use the normal distribution to figure out the probability of any hypothetical outcome. As I mentioned earlier, probability is tremendously important to inferential statistics. It's not that you necessarily need to actively think about probability distributions while you're running your t-test or your correlational analysis, but there's probability sort of going on underneath the hood when you run any inferential statistical analysis. This is because the basic approach when you run a statistical test is that you're going to evaluate that obtained outcome against the likelihood that it would occur by chance, given the null distribution being assumed to be true. This is the process that happens every time you subject your statistics to significance testing. The basic process of significance testing is to evaluate your obtained statistical outcome, be it a Pearson's R, be it a t-value, be it a chi-square, or the F from an ANOVA. You compare that obtained outcome to its underlying probability distribution. What you then do is you ask yourself, did my obtained statistical outcome have a really good chance of occurring on the basis of the null distribution? If the answer is that no, those odds aren't incredibly high, that's when we're able to conclude that we have legit effects. That's when we conclude that our outcomes are not just flukes, that they are actually not the result of the null distribution being true, but rather that it's more likely that our obtained statistics are probably the result of some genuine effect we have discovered. So that'll do it for my probability lecture. I hope you guys are doing well, and I'll talk to you soon.